Do you know a difference between function and function pointer? And you can pass function as a parameter to another function and create callback functions out of it. And moreover, you can even store functions in a vector. Yes, my friend. In this video, we are going to learn all these topics in detail, and by the end of this video, you will have a solid foundational understanding of how functions work under the hood in Rust and how you can utilize them to create safe and efficient Rust softwares. So with that said, let's get started in this video. So first thing first, let's understand what a function is. A function is a block of code that we write our set of instruction in, and upon calling that block of code, it will perform the set of instruction that we have given to it. So let's understand this. So let's say I created a function add, and add is supposed to add two numbers, right? And we are giving it two parameters x and y of type integers, and it will return back a sum of type integer, right? So let's say we have created this block of code add, and we named it add, right? And we want this add function to perform simple addition for us. So as you can see, we have created a named function over here using fn keyword, and we have provided two parameters to it, and it is returning us an integer value and doing a simple operation of addition, right? So this is a function here, right? So as you can see, this is a block of code that we have written, and we have given a set of instructions over here that hey, simply add these two value and return us the integer value over there. Now we can even pass the parameters over here. As you can see, I have passed x and y. Now this is a function, so it's very simple. Function is a block of code that we provide a set of instruction in, and upon calling that code, it performs that set of instruction for us, right? It may or may not return us the value, and it may or may not take input parameters. And the beauty of function is, let's say I have multiple code files where I need to use this function add. So instead of writing x plus y everywhere in the code wherever I need, I will create a function somewhere and reuse that function over the places where I need to call x plus y, right? So these functions let us help to make code reusable and modularize the code. Now let's understand what a function pointer is. So as you can see, I have defined a function over here. Now a function pointer, as a name suggests, it is a pointer, right? So please don't get confused this function pointer with the regular pointer, right? Let me just show you. So as you can see, suppose this is our memory. Let's name it memory, and I have defined a variable string. So let's say this is my variable string somewhere lays in memory, right? Now the string that I have defined, as I discussed in my previous video, a string consists of three things. First, a pointer that will point to its location in memory. Second, the size of that string, and third is the length, right? So all these three things are attached to a string, right? So a regular pointer, as you can see, will point to this location, memory location, right? So this is a pointer and it is a regular pointer, and this will point to a memory location of strings. But a function pointer will never points to a data, it will simply point to that functions in memory, right? So whatever we define, either a function or a variable, it lays in memory, right? So just like that, a function will also be in memory somewhere, and a function pointer will never point to its data, right? It will only point to that function. You understand? There is a difference between a normal pointer and a function pointer. A normal pointer will point to a location, and a function pointer will only point to that specific code of that function, right? So let's say this is function over here in memory add, right? It will only point to that function's code. Okay, the difference between function pointer and pointer is this. All right, so now let's create a function pointer. Let's say ptr, and it is of type fn that takes input i32 and return i32 and add, right? So as you can see, I have created a function pointer over here, right? This function pointer is of type fn, and i32 and i32, it takes two variable and it returns an i32, right? Just like this function. So this keyword here is used to create a function, and this keyword over here is a function pointer. All right, so this is how you create a function pointer. Let me just comment it over here. This is a function pointer. So few things to note over here. A function pointer should not be mistakenly considered as a normal pointer, because it is only pointing to that code of a function. All right, Now let's see the size of value of our pointer that we have created. So for that we will simply use a println statement, right? And we'll print out what is the size of the value of this ptr pointer that we have created. So we will use this mem crate over here of std, right? Std crate, and we will use a size of val. So as you can see, size of val. Now this will take a reference of that pointer, right? So this is ptr. So let's see what is the size of this, and we will compare it with the string, right? So now we are calculating the size of value of a function pointer, right? And after that we will create a string and use that pointer, and we will fetch the value out of it, right? So let's see how it goes. So let's open our terminal and cargo run. So can you guys guess what would be the answer over here? 8, right? So we got 8. Now what is this 8? Why we got 8? Like this function pointer is doing this, and why we got 8? Like we haven't passed anything over here, and this pointer, this size of val function, when we pass our reference of this pointer, it returned us 8. You see, 8 is actually 8 bytes, right? So it varies, and it based on a different system architecture, it will vary, right? So currently I have a 64-bit system architecture, so it is returning me 8 bytes, right? And in a 32-bit architecture, it will return 4 bytes. So it's very hardware specific thing, right? So it means that this pointer took 8 bytes in a memory, right? Now let's see what string holds. So let's create a variable called string, and it will hold string, right? Let's say it hello. So as I told earlier, that string has three components, right? Length and mem, size of val, and we will pass str. All right. So as I told earlier, that string holds three parts. One is the length, one is the size, and one is the capacity of that string, right? So let's see how it goes. And can you guys guess what would be the answer over here? You know what? Let me just give names over here, right? Uh, String over here, and let's say a function pointer. All right, let's open the terminal, cargo run. So as you can see, function pointer took 8 bytes, but string took 24 bytes. Now you connect the dots, right? A string has three components in it, and each component took 8 bytes, so it eventually adds up to 24, right? So this is the size of those pointer value in the memory that I have shown you, right? Now that you have known like how to create function and how to create function pointers, let's call this function pointer and call this function to see what is the difference while calling them. Okay, so to call a function, we simply call that function name, the parenthesis, and pass any input parameters if it has, right? So let's call our add function over here. So let's say println calling add function, right? And we'll call add, right? And we'll pass 2 and 3, right? So as you know, the expected behavior is simple. It will return a value 2 plus 3, 5, right? Now let's just call a function pointer over here as well. We'll say calling pointer, right? And we'll use ptr. So you see the difference? A function has been called by its name directly, and a function pointer to call that function because it is pointing that function's code, right? So in order to call that function, we have to indirectly call that function with the help of function pointer, right? So basically a function pointer is used to call the function indirectly. So to call that function add, we are using a function pointer, right? ptr, and we have passed these parameters in it. Let's see in terminal how it goes. Cargo run. As you can see, we have indirectly called function over here from function pointer, so we can even do that, right? There is a function that we have called directly, right? And we have called that function with the help of our function pointer as well. Okay, now that we have talked of a function with return types, let's talk about function that doesn't return anything. So let me just create another function over here, add no return. So it can perform a set of instruction but doesn't return anything, right? So in Rust, there are two ways, right? So as you can see over here, this functions by its signature. It seems that it doesn't return anything because we don't have this statement over here like this, right? But in Rust, if a function is not returning anything, it means it is returning a unit type, which is denoted by these parentheses. All right. So if a function is written like this and you see it, it means that it is returning a unit type or referred to void in some programming languages, right? So either you don't specify anything or you can specify this as well. They both are perfectly valid statements over here. Now, hey everyone, sorry to interrupt you in between. Just here for a few words. If you have reached this far, then please like this video, share it with your friends, and subscribe to my YouTube channel. And also, please stick in this video till the end. This video has a lot more information to offer, and also, please make sure to make notes or whatever you find useful. Okay, continue. Why I am doing this? Why I am showing you that this is a unit type and all? Let me just show you with a practical example over here. If I call this function that is not returning anything, right? Calling no return. Now let's see how it behaves. What does it return, right? So let's say add no return function over here. And you know what? Yeah, let's just create a pointer first over here, right? Uh, Function pointer to no return, right? And we create a function pointer ptr no, let's name it no, right? And its type is fn, right, equal to add no return. So this, you see, I have created a function pointer like this. Because it doesn't return anything, I can specify a simple fn over here with a parenthesis, right? And I can assign this add no return to this function pointer. So I have a function pointer of this add no return function, but I can do this as well. What I can do over here is I can specify it as it is returning a unit type like this, right? So they both are perfectly valid statement. Now let's see how does this pointer behaves, and how does this, and what will this pointer return if I use uh pointer no, right? This is what I have created, pointer no. Okay, let's open up our terminal. Can you guys guess what will it return? You see this. So it shows that if a function is not returning anything, it's actually returning a unit type, right? And this is a unit type, and that's why I have written that statement, that dash arrow and that unit type, right? So either you don't write anything or you can specify that it is returning a unit type. They both means perfectly same and they both are valid. And returning this unit type and not returning this unit type sometimes referred as void in some programming languages, right? So this main function as well also have a should have a like a function pointer that is called in Rust somewhere, that is a kind of entry point of this file, right? So this main function is the entry point of any Rust program. So Rust should be calling this mains function pointer somewhere, and that function pointer should be used to call these functions, right? So as you can see by now, what is the return type of this main function over here? It's unit type because it is not returning anything. If I do this over here, this would also be a perfect valid function, right? As you can see, there is no error. So as you can see by now that those who don't have any return type, they are actually returning a unit type. So now that we have learned these things, let's understand what are safe and unsafe function pointers in Rust. So everything we have written so far, every functions that we have created is actually a safe function, and the pointer that we have created to these are actually a safe function pointer. Now what does it mean by safe function pointer? So a safe function pointer means that it is written in pure Rust and that follows Rust ownership and borrowing rules and memory safety rules, right? Then it is a safe thing, right? And what is an unsafe function? We will create that unsafe function, but for now let's understand theoretically that an unsafe function is the one that doesn't follow Rust rules and it uses a keyword called unsafe. So as soon as Rust encountered that unsafe keyword, Rust will understand that okay, this program need to be unsafe. So basically what happens is Rust needs to be unsafe somewhere, right? It needs to be unsafe. Without an unsafe keyword, Rust is incomplete, because sometimes Rust needs to communicate with the external libraries also, right? So let's say via FFI, Rust communicate with C library, or if you are doing an embedded programming, Rust really want to contact that hardware, and for that, for compatibility, Rust needs to be unsafe, but it totally depends on the skill of a programmer while using an unsafe keyword, right? So what does unsafe means? Unsafe means that a programmer is solely responsible for its memory management, allocating and deallocating of memory, and all the thing that Rust should have taken care of. Now the programmer is responsible. So as soon as Rust encountered a unsafe keyword, it will simply run that program without validating all those memory rules and ownership and borrowing rules and all right. So now, as you can see, everything we have created so far is actually safe, right? Rust is keeping track of it. Now let's create unsafe pointers and functions. So as I told earlier, as Rust encountered an unsafe keyword, it will simply avoid all its checks and just perform the operation, right? So let me just show you what are the implications of writing unsafe code if you are not aware of what you are doing. So let's create an unsafe function over here. Unsafe. We'll use unsafe keyword to create unsafe function, and we will, let's say, create a risky add over here. It takes two parameters x and y of type i32 and will return an i32 value. Alright. So before going on to the implementation, let's create an unsafe pointer over here. So let's say let unsafe ptr of type, of course we'll use unsafe, right? And function pointer will denote how many parameter does it take and what it returns, right? And we will assign risky add to it. Now you see, you have created a unsafe function, you have created an unsafe pointer. Now the only thing that is remaining is an unsafe implementation. Now to understand what we are going to implement, let's go over here and see what we are going to do, right? So this is our memory, as you can see. So let's say here we have x somewhere in our memory, and as you know, if something is in a memory, then it have an associated address with it, right? A hexadecimal value. So what we're gonna do is, as you can see, we have some x variable in the memory, right? So if we have something in our memory, then it has a valid address attached to it, right? Some hexadecimal value. Now what we're gonna do is, we will change that hexadecimal value so that this x variable can move inside this memory, right? So currently it's here. If we update this hexadecimal value, it can go somewhere here, right? Somewhere here, somewhere here, somewhere. Now why I am doing this as an unsafe implementation? Because as you can see over here, I have used unsafe keyword right over here. Now it totally depends on the developer now that it passes a valid memory address. So let's see what all implications we can face over here after using unsafe, if we are not responsible enough to send a valid memory address or something like that. So let's do this. Let's get a raw pointer over here of this. Let's say a const i32. We will add some offset into it, y as usize, right? And let's dereference it in order to read its value. Now call this unsafe pointer to see what happens. Println, let's say unsafe pointer calling, right? And we will call this unsafe pointer over here, and let's pass 2 comma 3. You see, it requires an unsafe block. You see, now we are getting an error of call to unsafe function is unsafe, right? So see, Rust is making sure that you have defined an unsafe function, you have defined an unsafe pointer, right? But you cannot call it safe way, right? So we also need to call this inside an unsafe block. Yeah, you see, we have created an unsafe function. We are doing something like completely fishy over here. We have created an unsafe pointer, and inside the unsafe block we have created this unsafe code. Now let's see what an unsafe code in Rust can do if we are not aware of what we are doing. So I think we have saved this. Let's open our terminal and use cargo run. So as you can see, this is what unsafe code can do, right? You see, the thread main panicked actually at line 31. See, misaligned pointer dereference. Address must be a multiple of this, but and this, right? So you see, when a developer is not aware of what he is doing, then unsafe code can really be like, it's a dangerous thing, right? Because we don't even know what this x is. We don't even know if it's a valid memory address or not. Though we are sure that we are using adding an offset of like usize, but we don't even know like what x is, whether it's a valid memory address or not, right? So you see, this unsafe keyword has tricked Rust, or say just Rust has like give us a loose advantage over here, that you can run whatever you want, but always make sure to use unsafe keyword so that I will not be responsible, right? Question arise here is, why unsafe at first place then, right? Why unsafe in Rust? If Rust is so strict about everything, then why going unsafe? See, when you do an embedded programming, you see, sometimes you need to directly contact to the hardware, right? Or sometimes you need to directly access that pointer in the memory, right? Or maybe if you want to like contact an external C library, like where pointers are like widely used, then you need to go unsafe way just to make sure that okay, it should be compatible, right? So unsafe Rust is like designed that way, and you can read more about it. It's a very vast topic. So basically the gist of everything is Rust has to be unsafe for some specific task. So without unsafe Rust, we cannot do like embedded programming or something like that. So as you can see by this video, you have seen like what a function pointer is and how it's different from a function, how a function pointer is different from a pointer, and what are safe and unsafe function pointers. So before moving ahead in this program, let's address one more important thing. A unsafe pointer can contain a safe pointer, right? So because unsafe doesn't necessarily means that everything will go wrong, right? So an unsafe pointer can hold a safe pointer so as well. But a safe pointer will always and must necessarily should hold a safe pointer. Let me just show you. So we have created somewhere a safe pointer, right? This, so this ptr, right? Let me just do one more thing over here. I will update this line only. Let me just comment this. So let me create an unsafe pointer over here. Unsafe pointer, right? It will receive an unsafe pointer fn i32 expecting an i32 in return value. You see, now I'll do something very interesting over here. I will assign a save function to it. See, there is no error. Why? An unsafe function pointer can actually point to a save function, because it doesn't necessarily means that if it's unsafe then it will definitely go wrong. So this statement of saying that an unsafe pointer can point to a save function is perfectly valid, while the opposite is not, right? Let me just show you. Let me just create another, let's say a second ptr that only takes a safe pointer. All right, i32 and expected return value is i32. You see, I cannot assign a risky add function to it, because in Rust, safe means safe. A safe pointer cannot point to an unsafe function, but the opposite can happen, right? So this is the very important point to use. Maybe it can be asked in your interviews, right? So always remember that an unsafe pointer can point to a safe or unsafe functions, but a safe pointer will always and must point to a safe function. All right. With that said, we have enough of this theory, right? So let me revise it what we have done till now. So we have created function and we have created function pointer. We have called these two and we have understood what size does it hold in memory, right? And we have also compared it with string as well, right? Secondly, we have created some safe and unsafe code, and we have seen what are the implications of unsafe code writing if a developer is not aware of what he is doing. And we have seen one more interesting thing, that an unsafe pointer can point to a safe or unsafe function, but a safe function pointer will always point to a safe function. So with all the concept that we have learned so far, let's do a practical session and create some callback functions in Rust and do some unsafe programming safely. Before moving ahead and creating our own callback function, let's understand what a callback function is. So a callback function is a function that can be passed as an input parameter to another function and invoked later in some point of time. To understand this, let's imagine a scenario where you need to call an API and the result returned from that API is going to be used on that another function, right? So what you have done is you have passed that function as a parameter, and inside that function you have consumed that API and later implemented that result from the API into the passed function, right? So this is the callback function, and let's implement our own callback function. For that, we will create a simple function, something, right? This is a function signature. Now a callback function is one when we pass a function as a parameter, right? So let's create our function first, right? That we will call as a callback function. Let's name it print, and it takes an integer value, returns an integer value. So now we will pass this function as a parameter into another function. So this function is basically a callback function, right? So now let's call this function over here. Let's say let result equal to something. We have a function something and we will pass this print in it, right? And we'll see the what this print return, right? Callback function called result. All right, now we have passed this print on something. Let's take an input parameter over here. Let's name it callback. We will define a function pointer over here, right? Now this is a function pointer. It takes input parameter and it completely depends on this type, right? This print takes input parameter the same way this fn takes an input parameter, because this fn is actually a function pointer of this print function. Okay, and after performing some calculation, let's say a result equals, let's say 10 times 50 times 2, right? Let's do this and we'll return this callback and we'll pass a result into it. And as we have passed this, we are expected to return an integer value, because this callback function that gets called is actually returning an integer value, right? So let's save this function. Okay, now as you can see, we have created a print function over here, and this print function is actually a callback function, right? Because we have passed it as a parameter, and when we have passed it at a parameter, we will receive this as a function pointer, right? We cannot receive the actual function, right? Because the function pointer will actually point to that function in the memory, right? So this callback function input parameter has the type of function pointer, and this function pointer is actually returning an i32 value, right? So we have returned an i32 from here. After performing some calculation, we have called this function from here, right? Let's see how it goes. Save it, open our terminal, cargo run. So as you can see, the callback function has been called and the value is 1000, right? So you see how we passed function as a parameter to another function and later called after some calculation in the later point of time. So these are callback functions, right? These are very important when you will do async programming in Rust. You see, we took the help of function pointers, right? Because the functions are first class citizens and we can treat them as variable, we can store them, we can pass them as a parameter into another function, right? So actually the entire function is not passed, we use function pointer to pass that. So basically it's an indirect way to pass a function, because a function pointer will always point to a function somewhere in memory, right? So this is how we utilize the function pointer to create callbacks, right? Now let's move to a second example where we will implement an unsafe code. That's what we have learned, right? Safe and unsafe pointer. So currently what we have done till now is basically safe Rust, right? So this pointer over here, this function pointer over here is actually safe, right? Now on the second example, we will learn how do we implement an unsafe pointer and how we can do an unsafe programming in Rust. Okay. So before moving ahead with the next example, let me just demonstrate you what is the problem statement for our next example and how we are going to use unsafe Rust to do so. So the problem statement of our next example is we have an array and we need to get a raw pointer location of it, and we have to add an offset of 1, and we need to figure out how we can access the element of this array, right? So for that, let's create an unsafe function over here. Unsafe function, let's name it some unsafe function. All right, so our requirement is we need to create an array, get the raw pointer of 0th index, and then move one by one, like adding the offset of 1 and slowly traversing the array, right? So let's create an array. We'll use a vector macro over here and create a 5 element array. Right now the first requirement is getting the raw pointer of 0th index, right? So let's name it ptr and we'll use array dot as mute ptr. Now we are having, okay, we need to make this mutable. All right, so now what as mute ptr will return us is it will return something like this, and so a mutable pointer of i32, right? So it will return something like this, so that we can mutate this pointer, like add and offset and all, to traverse the array. Now let's so currently you see we are at the red dot, right? We have the raw pointer of 0th index, so we are at the 0th index or first element of that vector. Now we want to traverse the array, so we want the next element. So what we'll do is we will add an offset of 1 and our pointer will shift in this memory, right? So let's get the second element, that is ptr dot add. By adding an offset of 1, we are at the, we are supposing that our pointer is shifting, right? So print ln and uh, second element, right? And in order to access that value, we need to dereference it because it's in pointer, right? So let's call this function. Now in order to call an unsafe function, we have to use an unsafe block as well, right? From inside of unsafe block, we can only call this unsafe function. So we'll use some unsafe function and let's see what it does. So basically, let me just revise what it does. We have created an array just like this in memory, so it gets stored somewhere located in the memory. Now we need a pointer address of this 0th index, right? So as soon as we get the raw pointer address of this 0th index, we can traverse the array by adding an offset of 111, right? So currently it's here, we will add the offset of 1, the pointer will shift towards a first index or the second element. Now it did the same thing, right? It took the pointer, added an offset of 1, so we are assuming that the pointer shifts and we are dereferencing it to get the value. So let's run this code, hit cargo run. So as you can see, we are receiving the second element is 20. You see, the first element is 10, we are receiving the second element is 20. So something we should deduce from it is, while writing unsafe rust, a programmer has to like completely aware that okay, the address in the memory that he is receiving is a valid address. So if he receives a valid address, then he can add an offset of 1 and traverse the array, right? So unsafe rust is like this. So let's just get the third element as well. What we're gonna do is name it third as element, and we will add an offset of 2 right now over here, right? Dot add 2. So now that we have third element, let's see, the third element should come 30, right? So let's print ln third element. Third element, let's do a cargo run. We should get 30. No, exit. What we have done wrong, because we didn't dereferenced it. La la la. Okay, you see 30. Earlier we got the address in the memory, that hexadecimal value, right? So this way you can iterate array safely inside an unsafe block, but always be aware of what you are doing, right? I hope you guys have learned something from this video. If you like my work, please like this video and subscribe to my channel. Till then, stay happy, keep grinding. See you on the next one.